Hey there, and welcome back to the Sleepless Scientist. Tonight, we're embarking on a truly captivating journey, one that touches every moment of our existence. We're going to gently unravel one of the deepest mysteries in the universe. What is time, really? From the simple tick-tock of a clock to the tangled threads of our own memories, time shapes everything. But how does it flow? Does it bend? What happens to it in the most extreme corners of the cosmos or at the smallest scales of reality? We'll explore how our understanding of time has evolved, from ancient observations to Einstein's revolutionary ideas and even the perplexing world of quantum mechanics. It's a story blending science, philosophy, and pure wonder. So, settle in, get comfortable, and perhaps grab your favorite warm drink. Before we dive into this incredible mystery, a quick moment to ask, if you're enjoying our journey, please consider giving this video a like and subscribing to the channel. It helps us continue these explorations and it means the world. Thank you. Now, let's begin our story, not with complex equations, but with the very first whispers of time as humanity began to notice its rhythmic dance. Imagine our ancestors, long before cities and clocks, gazing up at the night sky. The moon waxed and waned, the sun rose and set, and seasons unfolded with predictable regularity. These celestial cycles were the first great clocks. Life itself was dictated by these rhythms. Planting, harvesting, migration all depended on understanding the passage of days, months, and years. Survival was intricately linked to this cosmic calendar. In ancient Sumer, around 4000 BCE, people developed one of the earliest calendars. Based on lunar cycles, it helped them organize their lives, their agriculture, and their spiritual practices. It was a remarkable step. The Egyptians, too, were master observers. They noticed the heliacal rising of Sirius, the brightest star, which coincided with the annual flooding of the Nile. This led to a solar calendar of 365 days, incredibly accurate for its time. Across the oceans, the Maya civilization created intricate calendars like the Long Count, capable of tracking vast spans of time. Their understanding of celestial mechanics was truly astounding, a testament to human ingenuity. These early civilizations weren't just measuring time, they were seeking to understand their place within its grand flow. Time wasn't just a sequence of events, it was a fundamental aspect of existence, often imbued with spiritual meaning. The desire to mark smaller intervals also grew. Sundials emerged, using the sun's shadow to track the hours of the day. A simple yet ingenious device, it brought the vastness of cosmic time down to human scale. But what about when the sun wasn't shining? Water clocks, or clepsydras, were developed. These devices measured time by the regulated flow of water, allowing for timekeeping even at night or on cloudy days. The accuracy of these early clocks was limited, but their invention marked a profound shift. Humanity was no longer just observing time, it was beginning to actively measure and segment it, striving for greater precision. This quest for precision would eventually lead to mechanical marvels, but first, a deeper question began to emerge. What asterisk is asterisk this thing we're trying to measure? Is it something real or just a human construct? The philosopher Augustine of Hippo in the 4th century famously wrestled with this. What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know. A profound admission. Augustine pondered whether time was a movement of bodies or something more fundamental. He concluded it was a distension of the mind, a subjective experience stretched by memory of the past and anticipation of the future. This idea of time as an internal experience rather than an external, objective reality was a powerful counterpoint to simply measuring its passage. It opened a philosophical chasm that still resonates today. Centuries later, the scientific revolution brought new tools. Galileo Galilei, observing the swinging lamps in a cathedral, noticed the regularity of a pendulum's motion, regardless of its arc. This was a crucial insight. Galileo's observation laid the groundwork for the pendulum clock, a device that would revolutionize timekeeping. It offered a consistent, reliable beat, far more accurate than any water clock or sundial. Christian Huygens, a brilliant Dutch scientist, took Galileo's concept and in 1656 built the first truly accurate pendulum clock. It was a marvel of engineering, reducing daily errors from minutes to mere seconds. The pendulum clock brought an unprecedented level of precision to human affairs. It enabled more accurate navigation at sea, better astronomical observations, and a more structured daily life. With the ability to measure time so precisely, the question of its fundamental nature became even more pressing. Was time just a series of nows following one another, or was it a continuous, invisible river? John Locke, the English philosopher, explored the idea of duration and succession. He argued that our idea of duration comes from observing the succession of ideas in our own minds. Time, again, linked to perception. This philosophical current emphasized that while clocks measured something, what that something truly was remained elusive. It was a dance between the objective measurement and the subjective experience. Then came Isaac Newton. His vision of the universe, articulated in his Principia Mathematica would profoundly shape our understanding of time for centuries. Newton proposed the concept of absolute, true, and mathematical time. He described it as flowing equably and uniformly, without relation to anything external. For Newton, time was like an invisible river, always flowing at the same steady pace, everywhere in the universe. It was independent of events, of observers, and of any physical measurement. This absolute time was the bedrock of classical physics. It provided a universal, unchanging backdrop against which all physical phenomena unfolded. It made the universe feel orderly and predictable. Newton distinguished this absolute time from relative, apparent, and common time, which is what we perceive through clocks, days, and years. Our measurements are just approximations of the true, underlying flow. This distinction was crucial. It meant that even if the universe were empty with no events to mark its passage, time would still flow. It was an inherent property of reality itself, a fundamental dimension. Newton's absolute time became the accepted view for over 2 centuries. It simplified physics, allowing scientists to describe motion and gravity with unprecedented accuracy, assuming a universal ticking clock. The feeling was that humanity had finally grasped time's true nature. From the unreliable rhythms of nature to the precise tick of a pendulum to a universal, absolute flow, progress seemed clear. Yet, even with Newton's powerful framework, the philosophical questions lingered. Was time truly separate from space? Could it be affected by anything? These seeds of doubt would one day blossom into entirely new theories. The Enlightenment era, with its emphasis on reason and observation, cemented this Newtonian view. Time was a constant, a stage upon which the drama of the universe played out, predictable and unchanging. But the universe, as we would eventually discover, holds far more surprises than Newton could have imagined. The calm, steady river of absolute time was about to encounter rapids and waterfalls. The very act of trying to measure time with increasing accuracy, of trying to understand light, would begin to reveal subtle inconsistencies with Newton's grand picture. Small cracks would start to appear. These seemingly minor anomalies, often dismissed at first, are the whispers that guide dedicated scientists to new frontiers. They are the universe's way of telling us there's more to learn. And it's in these whispers that our next chapter will begin. We'll leave the comfortable, predictable world of Newton and step into a realm where time itself becomes a flexible, dynamic entity, intertwined with space. As the night continues to unfold, we'll see how a young patent clerk named Albert Einstein dared to question the very foundations laid by Newton, forever changing our perception of time and space. The comfortable, predictable world of Newton, with its absolute time, began to show subtle cracks. Late 19th century physicists observed phenomena that didn't quite fit the established framework. One of the most perplexing puzzles involved light. Scientists believed light waves, like sound waves, needed a medium to travel through. They called this hypothetical medium the luminiferous ether. If the Earth moved through this ether, then the speed of light should appear different depending on the Earth's direction of motion, much like a swimmer moving with or against a current. In 1887, Albert Michelson and Edward Morley conducted a famous experiment designed to detect this ether wind. They built a highly sensitive interferometer. Their apparatus split a beam of light, sent the two halves along different paths, and then recombined them. Any difference in light speed due to the ether should create an interference pattern. But to their astonishment and the bewilderment of the scientific community, they found no such difference. The speed of light appeared constant, regardless of Earth's motion. This result was deeply unsettling. It meant either the ether didn't exist or the Earth wasn't moving through it, which seemed impossible. The foundations of physics were shaking. The constancy of the speed of light became a profound mystery. It defied common sense and the intuitive Newtonian view of space and time. It was into this intellectual ferment that a young Albert Einstein stepped. He wasn't seeking to explain the ether, he was ready to question deeper assumptions. Einstein's genius lay in accepting the constancy of light speed as a fundamental principle, rather than trying to explain it away with complex ether theories. In 1905, he published his theory of special relativity. Its two postulates were revolutionary. The laws of physics are the same for all non-accelerating observers, and the speed of light is constant for all. These seemingly simple ideas had profound consequences for time. If light speed is constant, then time itself must be flexible. Imagine two observers, one stationary, one moving rapidly. If they both measure the speed of light from a source, they will get the same result. For this to be true, something else must change. Einstein showed that time itself must slow down for the moving observer relative to the stationary one. This is time dilation. And not just time, lengths also contract in the direction of motion and mass increases. Space and time were no longer separate, absolute entities. Instead, they were intertwined, forming a single fabric called spacetime. Our perception of time and space depended entirely on our relative motion. The steady, universal river of time envisioned by Newton had become a series of currents, each flowing at its own pace depending on the observer's movement. This was a radical departure. It meant there was no single now for everyone in the universe. Events simultaneous for one observer might not be for another. Special relativity applied to constant velocity, but what about acceleration or the force that causes it, gravity? Einstein spent another decade grappling with this, culminating in his theory of general relativity in 1915. Here, gravity was not a force but a manifestation of spacetime itself. Massive objects like planets and stars warp the fabric of spacetime around them, much like a bowling ball placed on a stretched rubber sheet. What we perceive as gravity pulling objects together is actually them following the curves in spacetime created by other masses. And this curvature affects time too. Time flows more slowly in stronger gravitational fields. This is gravitational time dilation. If you were near a black hole where gravity is extreme, time would slow down dramatically for you relative to someone far away. A clock on Earth's surface ticks slightly slower than a clock in orbit because Earth's gravity is stronger at its surface. These were not just theoretical musings. Scientists began to devise experiments to test Einstein's audacious claims. One of the earliest confirmations came during a solar eclipse in 1919. Light from distant stars passing near the sun was observed to bend. This bending of starlight, exactly as predicted by general relativity, provided dramatic evidence for spacetime curvature. Later, in 1971, the Haefel-Keating experiment directly tested time dilation. They flew atomic clocks around the world on commercial airliners. Upon their return, these clocks were compared to stationary clocks on the ground. The flying clocks showed tiny but measurable differences. The differences precisely matched the predictions of both special and general relativity, accounting for both speed and gravitational effects. These experiments and many more since have confirmed that time is not an absolute, unchanging backdrop. It is a dynamic part of the universe. Our GPS systems rely on these relativistic corrections. Without them, the precise timing signals from satellites would quickly become inaccurate. This bending river of time, flowing differently for different observers and in different gravitational fields, fundamentally reshaped our cosmic perspective. Time became a dimension inextricably linked with space, forming a four-dimensional continuum, spacetime. Yet, even with this profound understanding, new questions arose. If time is so flexible, does it have a direction? Why does it always seem to move forward? Einstein's theories describe how time behaves, but they don't fully explain why we experience it as an arrow pointing from past to future. This mystery of time's arrow would lead scientists down another path, into the realm of thermodynamics and the concept of entropy. It suggests that the universe itself might be unfolding in a particular direction, driven by a fundamental law of increasing disorder. As the night deepens, we will gently explore this peculiar one-way journey of time and how it connects to the very fabric of our universe, hinting at even stranger cosmic phenomena. As the night deepened, our understanding of time's bending river led us to the edge of an even stranger frontier. The smooth, predictable universe of Einstein, while profound, didn't tell the whole story, especially when we looked at the smallest scales of existence. For centuries, scientists assumed that the rules governing the vast cosmos also applied to the tiny world of atoms and particles. But as the 20th century dawned, this assumption began to crumble, revealing a reality far more elusive. The early 1900s became a period of intense intellectual ferment, a time when radical new ideas were needed to explain baffling experimental results. It was the birth of quantum mechanics, a revolution in physics. One of the first unsettling discoveries was that energy itself wasn't continuous. Instead, it came in discrete packets or quanta, like tiny, indivisible units. This was a profound departure from classical physics, which viewed energy as a smooth, unbroken flow. It suggested that reality at its most fundamental level was granular, not continuous. Max Planck, grappling with the problem of black-body radiation, reluctantly introduced this idea in 1900. He initially saw it as a mathematical trick, a way to make his equations work. But the concept of quantization, of energy existing only in specific, allowed amounts, proved incredibly powerful. It hinted at a universe built from tiny, fundamental Lego bricks of energy. Niels Bohr extended this to the atom in 1913. He proposed that electrons orbited the nucleus only in specific, quantized energy levels, not just any orbit. When an electron moved from one level to another, it would absorb or emit a precise quantum of light. These quantum jumps were instantaneous and mysterious. This was the true dawn of quantum theory, a framework that described a world where particles behaved in ways utterly alien to our everyday experience. It was a murmur from the microcosm. Then came the unsettling revelation of wave-particle duality. Light, which we thought was a wave, sometimes acted like a stream of particles called photons. It defied simple categorization. Was it one or the other? The answer was impossibly both, depending on how you looked at it. Nature seemed to hold secrets in plain sight. Even more astonishing, this duality extended to matter itself. Electrons, protons, and all particles we considered solid things could also behave like waves. Louis de Broglie in 1924 proposed this matter-wave hypothesis. It was a bold idea, suggesting that everything in the universe possessed both particle and wave characteristics. The famous double-slit experiment performed with electrons dramatically confirmed this. Electrons, fired one by one, created an interference pattern, as if each electron was a wave passing through both slits simultaneously. This duality blurred the very definition of reality. A particle didn't have a fixed location until measured. It existed as a probability wave spread out in space. Adding to the strangeness was Werner Heisenberg's uncertainty principle, formulated in 1927. It stated a fundamental limit to our knowledge. You could know a particle's precise position or its precise momentum, but never both at the same time with absolute accuracy. The more precisely you knew one, the less precisely you knew the other. This wasn't about imperfect instruments. It was a deep, inherent property of nature itself. The quantum world refused to be pinned down with classical certainty. And then there was the observer effect. The act of measurement itself influenced the outcome. The quantum world seemed to choose a state only when observed. This probabilistic, uncertain reality of quantum mechanics was a stark contrast to Einstein's smooth, deterministic spacetime. Two powerful theories, yet seemingly at odds. This clash led to one of the most profound challenges in modern physics, the problem of time in quantum gravity. How could time exist in both these frameworks? In quantum mechanics, particles can exist in superpositions and tangled states where properties are undefined until measured. This makes a classical, flowing now difficult to define. Time, in standard quantum theory, often acts as an external parameter, a fixed backdrop against which quantum events unfold. It doesn't seem to be an active participant in the quantum dance. This is a key point of tension. Quantum mechanics treats time as something given, a steady beat from outside the system being studied. But Einstein's general relativity had shown us that time is dynamic, flexible, and warped by gravity. It's an integral part of the universe's fabric, not an external observer. How can time be a fixed, external parameter in one theory and a dynamic, internal component in another? This fundamental incompatibility is the core of the problem of time. Reconciling these two titans of physics, quantum mechanics and general relativity, requires a theory of quantum gravity, a quest that has captivated physicists for decades. One of the most audacious attempts was the Wheeler-DeWitt equation, developed in the 1960s. It sought to describe the quantum state of the entire universe. Its most startling implication was that the equation itself does not contain a time variable. It suggests that at the most fundamental quantum level, the universe might be timeless. If this is true, then time, as we experience it, isn't fundamental. It would be an emergent property arising from the complex interactions of more basic, timeless components. This shifts the mystery of time's arrow from a universal law to a consequence of how our consciousness interacts with a fundamentally timeless reality, a profound philosophical challenge. The Wheeler-DeWitt equation remains a highly theoretical and debated concept. It represents a frontier where our understanding of reality is pushed to its absolute limits. Yet research continues. Scientists are exploring quantum clocks, devices that try to define time using the very peculiar properties of quantum systems. There's also the intriguing idea that entanglement, the quantum phenomenon where particles become inextricably linked regardless of distance, might offer clues to time's nature. Even more recently, the concept of time crystals has emerged. These are not clocks in the traditional sense, but systems whose lowest energy state involves perpetual, repeating motion. Unlike regular crystals which break spatial symmetry, time crystals break time translation symmetry, meaning their behavior repeats in time without external input. They are a phase of matter that seems to tick on its own. The discovery and study of time crystals offer a tantalizing glimpse into how time might be fundamentally different in the quantum realm, perhaps even emerging from these intrinsic rhythms. The quantum murmur, this elusive dance of particles and probabilities, continually challenges our deepest intuitions about time. It whispers of a universe far more intricate and mysterious than we ever imagined. As we step out of the microcosm and look back towards the cosmos, these quantum riddles will become even more pronounced. For it is at the extreme edges of spacetime, in the heart of black holes, that quantum mechanics and general relativity clash most fiercely, offering us our next profound mystery. We've explored time's flexible nature and its elusive quantum dance. Yet, a fundamental question persists: why does time always move forward? Our daily lives are filled with irreversible events. A dropped glass shatters, a log burns to ash. We never see these processes spontaneously reverse. Most fundamental laws of physics allow for time to flow in either direction. A film of a planet orbiting a star looks equally plausible played forwards or backwards. Yet our experience is one of a relentless, one-way progression. This deep asymmetry is what physicists call time's arrow. To understand this arrow, we must journey back to the 19th century, to the dawn of thermodynamics and the study of heat and energy. In this era, engineers and scientists like Rudolf Clausius were intensely studying steam engines, seeking to understand how heat could be converted into work. Clausius observed a consistent, natural principle: heat always flows spontaneously from a hotter body to a colder one, never the reverse. This irreversible flow was a crucial insight. It suggested a fundamental directionality in the universe's processes. To quantify this universal tendency towards dispersal and equilibrium, Clausius introduced a new concept. He called it entropy. In 1865, he formally stated the second law of thermodynamics. The total entropy of an isolated system can only increase over time. In simpler terms, this law states that systems tend towards greater disorder or randomness. Order requires effort, disorder happens naturally. A hot cup of coffee left on a table will cool down. Its heat energy disperses into the cooler surroundings, increasing overall entropy. An ice cube melting in a warm room follows the same principle. The ordered ice structure breaks down, spreading coldness and increasing disorder. These everyday processes, driven by the increase of entropy, define a clear, observable direction for the flow of time. Without the second law, these events could, in theory, run backward, but our universe clearly forbids such reversals. Building on Clausius's work, the brilliant Austrian physicist Ludwig Boltzmann offered an even deeper, statistical interpretation of entropy. Boltzmann's profound insight was that entropy is directly linked to probability. Disorder is simply far more likely than order. Consider a box of gas particles. There's only one specific way for all particles to be neatly confined to one corner. But there are an astronomical number of ways for those same particles to be spread out randomly throughout the entire box. Disorder, therefore, is not a mysterious force, but a statistical inevitability. Systems naturally evolve towards these more probable arrangements. Boltzmann showed that the increase of entropy is not a fundamental law governing individual particles, but a statistical consequence of large numbers. The arrow of time, then, is essentially the universe moving from less probable, ordered states to more probable, disordered ones. It's why an egg breaks but doesn't spontaneously reassemble. There are countless broken states, but only one whole state. This statistical view profoundly clarified time's unidirectional flow, linking it to the sheer mathematics of probability. The universe, in its relentless pursuit of higher probability, constantly explores new, more disordered configurations. With each step, time moves forward. But if the universe is always increasing in disorder, how did it start in such an incredibly ordered state to begin with? This question leads to one of cosmology's most profound ideas, the past hypothesis. It proposes that the early universe, just moments after the Big Bang, was in a state of exceptionally low entropy. This highly ordered, improbable initial condition is believed to be the ultimate origin of the thermodynamic arrow of time we observe today. The Big Bang wasn't just hot and dense. It was remarkably smooth and uniform, a state of immense potential for disorder to grow. As the universe expanded, it created more and more possible configurations for matter and energy to occupy. This increasing phase space or number of available microstates allowed entropy to steadily climb from its initial low value. Our entire cosmic history, from the formation of stars to the emergence of life, is a journey of increasing entropy and unfolding from that initial order. The universe is still unwinding from this extraordinarily improbable, low-entropy beginning. The past hypothesis explains why we experience time flowing forward from that point, even if it doesn't explain why the universe started this way. This relentless march of entropy is visible everywhere in our lives, a constant reminder of time's direction. A magnificent sandcastle left to the elements will inevitably crumble and disperse, its ordered structure giving way to random grains. A freshly brewed cup of tea cools and the sugar dissolves uniformly, never reforming its crystalline structure spontaneously. The human body, a marvel of complex order, also succumbs to the arrow of time, experiencing aging and eventual decay. Entropy defines the fundamental asymmetry of our existence, giving time its one-way street. Yet the universe holds even stranger places where this arrow might bend or even cease to point, places like the heart of black holes, our next destination. The arrow of time, defined by entropy's relentless march, guides our universe. Yet, at its most extreme edges in the heart of cosmic behemoths, this arrow begins to twist, challenging our deepest intuitions. Our journey now takes us to these profound cosmic chronometers. These are black holes, regions where gravity is so intense that nothing, not even light, can escape. They represent the ultimate test of Einstein's theories and a place where time itself takes on a bewildering new character. The existence of black holes was first predicted theoretically, a startling consequence of Albert Einstein's general theory of relativity. His equations, when pushed to their limits, pointed to these gravitational singularities. Just months after Einstein published his theory in 1915, Karl Schwarzschild, a German physicist serving in World War I, found a precise solution to Einstein's equations. His solution described the spacetime around a perfectly spherical, non-rotating mass. Schwarzschild's work revealed a critical boundary now known as the Schwarzschild radius. If a mass is compressed within this radius, its gravity becomes so immense that it forms a black hole. This boundary is the event horizon, the point of no return. Cross it, and you are irrevocably committed to falling into the black hole's singularity, where spacetime itself is infinitely curved. From the perspective of an observer far away, something truly strange happens to time as an object approaches the event horizon. It appears to slow down dramatically. Imagine a clock falling towards a black hole. To an external observer, the ticks of that falling clock would become slower and slower, its light growing redder, stretched by gravity. As the clock reached the event horizon, its ticks would appear to stop entirely. The light it emitted would be redshifted infinitely, fading from view. From outside, it would seem to freeze in time. But for the object itself falling across the event horizon, time continues to flow normally. There is no special sensation upon crossing. The point of no return is just another location in warped spacetime. Once inside, all paths lead to the singularity. Space and time effectively swap roles. Moving forward in time means moving towards the singularity, an unavoidable destination. Black holes thus become cosmic laboratories where the extreme bending of spacetime reveals the profound flexibility of time itself, far beyond our everyday experience. For decades, black holes were considered perfect cosmic traps, swallowing everything and never letting anything out. But then, a new puzzle emerged, linking them to the quantum world. In the 1970s, Stephen Hawking, along with Jacob Bekenstein, made a groundbreaking discovery. Black holes have entropy, a measure of their disorder. If black holes have entropy, then according to the laws of thermodynamics, they must also have a temperature. And if they have a temperature, they must radiate. This led to the astonishing prediction of Hawking radiation. Black holes, it turns out, slowly leak particles and energy, eventually evaporating over vast cosmic timescales. Hawking's work brought together gravity, quantum mechanics, and thermodynamics, three pillars of physics, into a single, profound context, revealing a deeper connection in the universe. This radiation also posed a deep paradox. What happens to the information of the matter that falls into a black hole? Does it truly vanish, or is it encoded in the radiation? While black holes challenge our understanding of local time, the universe as a whole also possesses a grand, overarching cosmic time. This began with the Big Bang. The Big Bang theory describes the universe's origin as an extremely hot, dense state approximately 13.8 billion years ago, from which it has been continuously expanding and cooling. This expansion provides a universal clock. By observing the redshift of distant galaxies, we can measure how long light has been traveling and thus how old the universe is. In a sense, the universe itself acts as a giant chronometer, its expansion dictating a shared timeline for all observers, despite local relativistic effects. From the first moments of the Big Bang through the formation of stars, galaxies, and planets, cosmic time marks the unfolding story of everything. The discovery of the universe's accelerated expansion, driven by mysterious dark energy, added another layer of complexity to our cosmic timeline. This expansion and the properties of dark energy will ultimately determine the universe's fate and, with it, the ultimate destiny of time itself. Scientists have proposed several scenarios for the universe's ultimate end, each with profound implications for the very nature and continuation of time. The most widely accepted scenario is the Big Freeze or heat death. Here, the universe continues to expand, stars burn out, and matter eventually decays into a cold, dark, and empty void. In this scenario, entropy reaches its maximum. All energy is uniformly dispersed and no further work can be done. Time, in a meaningful sense, would cease to have direction or purpose. Another possibility, if gravity eventually overcomes the expansion, is the Big Crunch. The universe would reverse its expansion, contracting back into an incredibly hot, dense state, perhaps leading to another Big Bang. In a Big Crunch scenario, time might effectively reverse or loop, bringing the universe back to a state similar to its beginning. The arrow of time would bend back on itself. A more extreme scenario is the Big Rip, where dark energy's influence grows so strong that it eventually tears apart galaxies, stars, planets, and even atoms themselves. In this cataclysmic end, the very fabric of spacetime would unravel, and our familiar concept of time would likely lose all meaning as existence itself fragmented. These cosmic fates force us to confront the ultimate questions about time. Is it an eternal river, or does it have a beginning and an end? Is its flow inherent or a property of the universe's evolution? We exist in a unique moment of cosmic time, billions of years after the Big Bang, with stars still burning and galaxies still forming. Our present is a fleeting instant in this grand narrative. The very act of observing these distant cosmic events is an act of looking back in time, seeing galaxies as they were billions of years ago, a direct connection to the universe's past. From the immediate present to the unimaginable future, time acts as a profound, dynamic dimension, shaping the destiny of stars, galaxies, and perhaps even consciousness itself. Even with these vast cosmic perspectives, the fundamental nature of time remains elusive. It is not merely a measurement, but an intrinsic part of reality's unfolding. From the quantum murmur to the cosmic roar, time weaves a complex tapestry, connecting the smallest particles to the largest structures, the briefest moments to the longest eons. As we contemplate these cosmic chronometers and the universe's ultimate fate, we realize that our understanding is still incomplete. There are deeper layers to peel back, more profound questions to ask. And it is in this realization of the vast unknown and our place within it that we turn towards the very subjective experience of time and how our minds construct the now amidst the cosmic flow. Our final chapter awaits. We've journeyed through time's many faces, from the personal tick of our internal clocks to the grand cosmic sweep. It has been a profound exploration. We began with our ancestors, observing the sun and moon, building the first calendars, connecting time to the rhythmic pulse of nature. Then came the philosophical puzzles, Augustine wondering what time truly was, a distension of the mind, deeply tied to human perception. Newton gave us absolute time, a universal, unwavering river, a comforting and predictable backdrop for the entire universe. But Einstein revealed its fluidity, a bending river in the very fabric of spacetime, slowing near gravity's powerful embrace. We delved into the quantum murmur, where time's role grew elusive, becoming a parameter rather than an active, dynamic player. The uncertainty principle and wave-particle duality hinted at a reality where time might not flow as smoothly as we perceive it. Then, the arrow of time, guided by entropy, explained why broken glass never reassembles and why the universe expands towards disorder. And finally, to cosmic chronometers, black holes, where time seemingly stops at the event horizon for distant observers, a profound gravitational effect. The universe's grand timeline, from Big Bang to potential Big Freeze, showed time as an epic story, with its own cosmic beginning and perhaps an end. Despite these profound insights, a fundamental tension remains. the smooth, curved spacetime of general relativity clashes with the granular, probabilistic world of quantum mechanics. This is the problem of time at its core. How can time be both a dynamic part of the universe's fabric and a fixed, external backdrop? To resolve this, physicists seek a theory of quantum gravity, a grand unification that would describe gravity at the quantum scale. Theories like string theory propose that fundamental particles are not points, but tiny vibrating strings operating in higher dimensions. In this view, gravity itself emerges from the vibrations of these strings, potentially offering a quantum description of spacetime uniting forces. Another contender, loop quantum gravity, suggests that spacetime itself is not continuous but made of discrete, interwoven loops. If spacetime is quantized, then time, as we know it, would also emerge from these fundamental atoms of space and time. Such a theory could transform our understanding, potentially revealing that time, at its most fundamental level, is not what we perceive. It's a quest for the very bedrock of reality, where the concepts of before and after might dissolve into something more profound. This search for quantum gravity continues, a testament to human curiosity, pushing the boundaries of what is knowable about time's ultimate nature. Beyond the equations, philosophy grapples with time's essence. Is only the present moment, this now, truly real? This view, called presentism, aligns with our direct experience. The past is gone, the future yet to be, only now truly exists. But many physicists influenced by relativity lean towards eternalism, often called the block universe theory. In the block universe, all moments, past, present, and future, exist simultaneously, like frames in a cosmic film laid out forever. Our perception of time's flow, then, would be an illusion, a conscious journey, or perhaps a slice moving through this pre-existing block. This perspective is deeply unsettling for some, challenging our notions of free will and the very nature of becoming. If all moments already exist, does our future simply unfold along a predetermined path, or is there still agency? Yet, relativity's lack of a universal now lends strong support to this timeless, four-dimensional block, where all events are equally real. The debate between presentism and eternalism is not just academic, it touches on our most fundamental beliefs about existence. It asks whether time is a fundamental aspect of reality itself, or merely a profound construct of our perception and consciousness. After this long journey from ancient calendars to cosmic destinies, one truth stands clear: time remains profoundly mysterious. We have gained incredible knowledge, mapping its bends, its arrows, its quantum whispers, yet its ultimate essence still eludes us. The universe is still whispering its secrets, prompting us to ask deeper questions, to look beyond the obvious, to never cease our inquiry. This ongoing inquiry, this relentless pursuit of understanding, is perhaps the most beautiful aspect of our scientific journey. It is a testament to human curiosity, to our innate desire to comprehend the intricate fabric of reality, even when it resists easy answers. Time, in its many forms, is not just a dimension. It is the very medium through which existence unfolds, connecting all things. It is the rhythm of our lives, the canvas of our memories, the engine of cosmic evolution, a constant presence. And as we close this chapter and this story, we recognize that the greatest mysteries often contain the greatest beauty and inspiration. The quest for time's true nature is far from over. It is an open invitation to continue exploring, to keep wondering, to embrace the unknown. And so, as the moon climbs high, sleep well, knowing that the universe and time itself holds endless wonders, waiting patiently for our next waking thought.